Section: Introduction. In this section, we delve into the realm of large language models, LLMs, and their capabilities in solving natural language and code generation problems. While transformers have made strides in these areas, they still face challenges when it comes to complex multi-step reasoning tasks without external tools. To investigate algorithmic reasoning, we focus on simple arithmetic problems like addition in a controlled laboratory setting. Addition serves as a suitable test case as it is simple enough for modest-sized LLMs to learn from scratch but challenging for large models without additional support. By training transformers on arithmetic tasks, we aim to understand the architectural choices, dataset characteristics, and training methods needed for multi-step reasoning processes like multi-digit addition. Our experiments reveal that transformers struggle with addition due to difficulties in precisely representing the position of digits within a sequence. To address this issue, we introduce abacus embeddings, which are learned positional embeddings designed to encode digit positions within numerical tokens. By combining abacus embeddings with standard positional embeddings, we observe significant improvements in accuracy. Models trained with this approach can generalize from 20-digit to 120-digit addition problems, showcasing a state-of-the-art generalization factor of 6 times. We explore various techniques to enhance arithmetic and generalization in transformers. Input injection, skip connections between the input layer and decoder layers, reduces generalization errors by 50% compared to the abacus embedding baseline. Additionally, loop transformer architectures, incorporating recurrent layers with shared parameters, achieve near-perfect generalization on addition tasks. Building on our success with large addition problems, we extend our methods to multiplication and sorting tasks, demonstrating length generalization techniques that transfer across different algorithmic tasks. Our contributions include the introduction of abacus embeddings for improved digit significance representation, leading to near-perfect generalization. By combining these embeddings with input injection and loop transformers, we achieve a substantial increase in out-of-distribution accuracy. In summary, our work pushes the boundaries of length generalization in arithmetic tasks and extends these findings to more complex algorithmic problems like multiplication and sorting. Our approach showcases significant advancements in LLM capabilities for algorithmic reasoning without the need for external tools. Section Summary. In this section, we explore the challenges large language models, LLMs, face in performing complex multi-step arithmetic reasoning tasks without tool use. By introducing abacus embeddings and incorporating input injection and loop transformer architectures, we significantly improve the generalization of transformers in solving large addition problems, achieving a state-of-the-art generalization factor of 6 times. These enhancements not only extend to multiplication and sorting tasks but also demonstrate the potential for extreme length generalization techniques to transfer to other algorithmic learning domains. Section: Positional Embeddings. In this section, we discuss the importance of positional embeddings in transformer models for language modeling. We start by explaining absolute positional embeddings, APE, and how they are added to token embeddings before the first layer of the transformer. However, APEs have limitations in length generalization. To overcome this, we introduce relative embeddings, RPE, which are embedded during attention computation, a concept further simplified by other researchers. Several works, such as Sandwich, Kerpel, and Alibi positional embeddings, have built upon these ideas to enhance length generalization. Moreover, we demonstrate that decoder layers can still learn positional information effectively even without explicit positional embeddings, known as no-positional embeddings, NOP. NOP performs well for small algorithmic tasks and can even outperform specialized embeddings in some cases. Rotary positional embeddings, ROPE, are commonly used in modern transformers, but they may limit length generalization due to being trained solely on rotations based on the length of the training data. For improved length generalization, post-training extensions can be added. One notable extension, functional interpolation for relative position embeddings, FIRE, has shown significant improvements in length generalization, particularly in arithmetic tasks like addition. When combined with randomized embeddings, FIRE can enhance length generalization by 2.5 times for addition tasks. We delve into more details on these positional embeddings in the appendix. In our study, we focus on NOPE and FIRE embeddings as they have shown to be the most effective for addition tasks in reversed format among existing embeddings. Section Summary. In this section, we explore various positional embeddings for improving the arithmetic capabilities of language models, focusing on NOPE and FIRE embeddings as they excel in addition tasks in reversed format. We train decoder-only causal language models for addition problems without padding between digits or adding zeros to operands, achieving strong length generalization. Our experimental setup involves training on all combinations of operand lengths, using a language model cramming setup, and reporting accuracy for different length pairs, including extrapolation instances, across in distribution, out of distribution, and extreme out of distribution evaluation categories. Section. Abacus embeddings help align digits. In this section, we observed that standard transformers struggle with learning multi-digit addition, even when the input numbers are presented least significant digit first and there is abundant training data available. We noticed that humans align digits of the same significance into columns when performing long addition. Our hypothesis is that transformers find it challenging to represent the significance of each digit's position relative to the beginning of the number, which makes it harder for them to solve addition problems. Previous approaches have tried to solve this issue by adding explicit index hints in the inputs and outputs of addition problems. However, using these index hints increases the input context length required and doubles the output length and inference cost, making it less efficient. Additionally, models trained with index hints are sensitive to random initialization, affecting their ability to generalize. To overcome these limitations, we introduced abacus embeddings, a specially designed positional embedding that encodes the location of each digit relative to the start of the number. These embeddings help the model align digits by providing a clear signal for positional information. We used consecutive ascending indices with a random starting position to allow for better generalization. Abacus embeddings significantly improved the generalization performance of standard transformer architectures for addition problems with up to 100 digits. By training on larger datasets, we found that the performance of the models improved, even for operands with fewer than 100 digits. Next, we explored the use of recurrent architectures to further enhance the transformer's ability to perform multi-digit addition. We introduced recurrent blocks and recurrences to improve the effective depth of the transformer. Input injection, which involves propagating a copy of the input to each layer in the network using skip connections, was also employed in our experiments. Section Summary. In this section, we observe that standard transformers struggle with learning multi-digit addition, especially when digits are presented least significant digit first. We hypothesize that transformers find it challenging to represent the significance of each digit's position relative to the beginning of the number. To address this, we introduce abacus embeddings, a specially designed positional embedding that encodes the location of each digit relative to the start of the number, significantly improving generalization performance for addition tasks up to 100 digits and beyond for standard transformer architectures. Section. The benefits of recurrence. In this section, we compare different architecture variants using both FIRE and NOPE embeddings trained on addition with operands up to 40 digits. Despite having significantly fewer parameters, the looped transformer achieves the best out-of-distribution performance. We can adjust the number of recurrences during training to improve generalization, known as progressive loss computation. By varying the size of the recurrent block while keeping the effective depth fixed, we observe further performance improvements in some cases with the combination of recurrence and abacus embeddings. For multiplication tasks, we make adjustments to the setup and find that abacus embeddings help achieve near-perfect accuracy. When sorting arrays of numbers, we see that the combined embedding approach enhances the model's generalization ability. The abacus embeddings show superior performance in sorting tasks, indicating their potential for a wide range of algorithmic tasks beyond basic arithmetic. Section Summary. In this section, we compare different architecture variants using both FIRE and NOPE embeddings trained on addition problems with up to 40 digits. Despite having significantly fewer parameters, the loop transformer model achieves the best out-of-distribution performance, especially when varying the number of recurrences during training. Additionally, we explore the application of these models to more complex tasks like multiplication and sorting, where abacus embeddings show promising results in enhancing generalization abilities, particularly in challenging scenarios like array sorting. Section: Abacus and Relative Embeddings. In this section, we explore how abacus embeddings can be integrated with other relative embeddings to enhance performance on various tasks beyond arithmetic. We find that combining abacus embeddings with techniques suitable for natural language tasks can be beneficial for large-scale models. While most current models use rotary embeddings, which are not ideal for length generalization, we show that combining abacus embeddings with rope can improve performance in handling operand length variations. Moreover, our experiments reveal that integrating abacus embeddings with FIRE can significantly enhance generalization capabilities, surpassing what FIRE embeddings can achieve alone. We assess the potential of abacus embeddings in a broader system context, demonstrating improved performance in tasks such as multiplication and variable length array sorting. Moving on to the discussion and limitations, we acknowledge the advancements in language models, LLMs, for complex tasks like code generation and mathematical reasoning. However, pushing these models to their limits remains a challenge. We focus on mathematical reasoning tasks such as addition, multiplication, and sorting to evaluate the capabilities of specialized language models in a controlled environment. Our study investigates the ability of language models to learn algorithmic tasks without external tools, emphasizing architectural enhancements like improved embeddings and recurrent layers. The inclusion of abacus embeddings in standard transformers and recurrent models leads to significant performance improvements, particularly in length generalization tasks. We achieve remarkable results in extrapolating tasks, such as addition of up to 100 digits, showcasing the synergy between abacus embeddings and other relative embeddings like FIRE. Our experiments go beyond simple length generalization, presenting modifications that enhance performance across multiple algorithmic reasoning tasks simultaneously. Despite the progress made, our study has limitations, including constraints on compute resources. While we demonstrate the compatibility of abacus embeddings with other embeddings, our focus remains on numerical tasks. Future research should explore the performance of abacus embeddings on a wider range of tasks, including both numerical and natural language inputs.